Okay, guys. So in the previous class, which Dheeraj sir took, I think you were discussing, you know, moment of inertia. Yes, guys,
Yes, sir.
right? Did you guys talk about the parallel axis theorem and the perpendicular axis theorem?
No, sir. Sir told us that it has to be done this class.
Okay, cool. So we'll start from there, and we'll also talk about other stuff apart from those. Okay, but let us start from how do you find out moment of inertia for like I had given you a list, and I think Sir also discussed a few moment of inertias, right? I am expecting that all of you will remember the basic formulas, okay? And if I list out those formulas, these are the minimum number of formulas that you have to remember. Like for example, you can see my screen, I believe, right?
Yes, sir.
So if you have a rod of mass m and length l, right? And it's rotating about this center, then the moment of inertia is ml square by 12. It's ml square by 12. The same rod, if you try to rotate it by holding by fixing one end instead of fixing the center, if you hold it on one end and then rotate it, guys, tell me what is the moment of inertia if this mass is m, length is
That
l?
will be mn square by 3.
It's going to be ml square by 3. The next important thing is obviously the point mass. If there is just one point mass which is at a distance of, let's say, r, and its mass is m and it's rotating about this axis of rotation, what will be its moment of inertia, guys?
That will be mr square.
It's just mr square, right? What about a ring? What about a ring? Now ring has all its mass concentrated only on the periphery, right? If you have a ring like this, okay, and the ring is rotating about that central axis, right, like this. So again, this mass of this ring is m, and the radius of the ring is r. So can you tell me what is the moment of inertia of this ring?
That will be mr square.
Mr square. What about a disk, guys? Now what is the difference between a disk and a ring?
The disk is a 2D planar shape.
Yeah. Well, if you can just say that if the mass is spread out throughout the entire, entire area, there is something we call a plate or a disk, whichever both the terms are okay, right? But if the mass of this disk is m and the radius is r, then the moment of inertia of a disk about its central axis is mr square by 2. Notice how I'm each of the time I am talking about moment of inertia, I'm always mentioning it is about which axis. Remember, in rotation, whenever we are talking about torque or moment of inertia, please understand they are exclusively defined only for a certain axis. So it is vital that you mention what moment, like which axis you're finding out the moment of inertia about. Okay. Now, once you are done with this, what about a hollow cylinder? Hollow cylinder. An example of a hollow cylinder will be an empty can. Empty can.
That will be mr square.
It will be same as the ring mr square. The reason for that is because you can think of like if you cut a small part out of this hollow cylinder, you're gonna end up with a ring only, right? So if you add up all those small rings throughout this hollow cylinder, the moment of inertia will be the mass of this entire hollow cylinder and the radius square, so mr square. Okay, so the radius of this thing is r. What about a solid cylinder? What about a solid cylinder, guys?
That will be mr square by 2, just like a disk.
Awesome, it's mr square by 2.
So what is the application of finding moment of inertia?
That's what we're going to discuss after this. I just have two more and then we are done. If you have a hollow sphere, what is the moment of inertia?
2 by 3 mr square.
2 by 3 mr square. And the last one is the solid sphere, whose moment of inertia is 2 by 5 mr square.
So in the last class, we had derived all these, but except the last two. Dheeraj sir told that we can derive hollow sphere by considering it as rings. So how to do it? Could you just show it in case it's possible?
Okay, sure. I'll give you a hint. Again, the integration of this can be found in any standard textbook. You can find it even in your module. So I'll give you a head start. You can ask me doubts later on again on if you are struggling at a certain step of that. Okay, so what you can do is at an angle of theta, you consider a small angle d theta. Okay, now let me make it a little bit big so that you're able to understand. Let me insert a sphere also. Okay, and also let's get rid of the fill. And the outline needs to be a little bit heavy. Cool. So this is like a hollow sphere. So what we are going to do is from the center, we are going to consider this as the x-axis. This is where the origin is, and this is about which we are going to do this entire integration, right? So at an angle of theta, Rishi, what we are going to do, and it is relevant for everyone, not just Rishi. So please let me know if you have any doubt. Okay. Guys, at an angle of theta, we're going to take a small element d theta. See, all of the time when we did this integration, it's all the time at a distance of x, we take dx. But if you do that, in this case, the integration becomes very, very difficult because it's a sphere. A much easier approach would be to, essentially take at an angle of theta, a small angle d theta. Now, how does it help us? Well, if you know the angle, now remember this from the first few classes that we did. If we know this angle theta and the radius is r, do you remember how much this length is? Guys, come on.
That will be r d theta.
R into theta, right? So here again, the radius is r, but the angle between them is d theta. So guys, this length right here is nothing but r d theta, r d theta. Okay. So guys, any doubt till here? Please let me know. Also, let me hear you guys. Is everyone there? One second. Let me quickly take the attendance just in case. Shankar Datta. Well, that's me. Ishani.
Yes, sir.
Janvi.
Yes, sir.
Medha.
Yes, sir.
Namish.
Present, sir.
Purva.
Yes, sir.
Vidya.
Yes, sir.
Rishi.
Yes, sir.
Ritika.
Yes, sir.
And Ritu.
Yes, sir.
Well, you guys are here, then why am I only hearing just Rishi all the time? Okay, guys, please participate. This is your class as well. Okay, participate and talk to me. Okay, you can watch videos in YouTube also. Why are you here to just watch the video? You're here to interact, right? See the difference. Okay, understand the difference between an online class and a video. Okay, if you treat me just like a video, just talking to, this, I don't know. You get what I'm trying to say. So I'll just plug this in the attendance group. Okay. So this is the integration of hollow sphere. Let us continue. Okay. So after we have considered this, what we are going to think about next is essentially a ring like this. Okay. And I'm going to try my best to make this properly. It's a sphere. So this is how it will look. Like if I extend this strip in 3D, this is how the strip would look. Are you able to understand? From the top, this is how it will look. This is how the ring would look. This is the ring inside. Okay. So from the top, this is the sphere and this is the ring. Okay. And this thickness right here is how much? R d theta. Please let me know if you understood the, the significance of this.
Yes,
Guys,
sir.
you understood this? Now, it's not going to help us to not just define the element. We also have to find out the mass of this element because it's ultimately the moment of inertia of that ring would be mr square because it's a ring. So mr square, but its length, mass will be dm. So dm into its radius square, small r square. Okay. Now, if you consider this triangle, this length is r. So can you tell me what is the radius of the ring that I have chosen? Like the radius will be same as this, right? Like this length will be same as this length, right? So guys, can you tell me what is this radius small r? It's going to be capital R cos theta, I believe, because it's a 90-degree towards theta cos theta. So in this formula, all you have to do is dm into r cos theta ka whole square. Okay. Now, one last question: How do you find out dm? Well, in a hollow sphere, you can think the total area. The total area is what? Total area of a sphere.
That will be 4 pi r square.
4 pi r square, right? So unitary method, 4 pi r square has capital M mass, and the area of this strip, if you think about it, like if I open this shaded strip like this, guys, can you tell me what is the thickness of this? Well, the thickness is r d theta, but can you also tell me what is the length of this shaded strip? Well, it's going to be 2 pi small r, and small r is capital R cos theta, so 2 pi r cos theta. So guys, tell me what is this area of the strip? Well, 2 pi r square cos theta d theta will have how much mass? Dm mass. Now, if you remember unitary method, dm will be equals to how much? Cross multiply and equate. So m into 2 pi r square cos theta d theta divided by, guys, divided by 4 pi r square. Now, this is how you get the value of dm. And after you find out the value of dm and plug it here, r cos theta square, and then you perform the integration with respect to theta, right? Now, Rishi, can you tell me what will be the limits on theta though? Because if you're integrating with respect to theta, it will come, I think, cos cube.
That will be from 0 to 2 pi.
No, if you do from 0 to 2 pi, then your first ring will be like the biggest ring here. And as you go up, as the angle increases, and then when it decreases again, you'll be counting it twice. So please understand, you have to do the integration in such a way that rings, you take rings from the bottom of the sphere to the top of the sphere so that it covers the entire thing. So tell me, if I try to take a small ring here, what should be the angle? What should be the angle theta? Well, it should be minus pi by 2. When theta is minus pi by 2, you'll be talking about a small element at the bottom of this hollow sphere. Let me draw it for you. So if you take the first ring here, the next ring here, the next ring here, next ring here, and so on, when you reach the highest point and complete the integration, what will be the value of theta?
The pi by 2.
Yes. So your integration on d theta will have limits from minus pi by 2 to plus pi by 2, right? So the only thing you need to do is now do the calculations. Okay. Do the mathematical calculations behind it. Everything else I have talked about. Okay. So give it a try. If you get stuck in any particular step after this, please let me know. I'll explain. I'll explain. Okay. So I hope you understood this one. Let us move forward into the next segment of this, which is what exactly is the understanding of moment of inertia, right? What exactly do you understand from moment of inertia? So for that, what I'm gonna need is the handy dandy simulator. Okay. So hold for 2 seconds while I switch to a website. Okay, so it was in moment of inertia, right? So rotation. Yep. Got it, guys. Got it. Now I need to just share my different screen. New share. Okay. Guys, please let me know if you don't understand any part of this. Okay. So this is an inclined plane. Have you done this before? Please let me know if you have done this.
I don't think we have done this before.
Okay, cool. So guys, listen to this. I have an inclined plane. I have an inclined plane with a certain angle, and there are 4 bodies on top of it. You can see there's a solid cylinder, there's a hollow cylinder, there is a solid sphere, and there is a shell, which is essentially a hollow sphere. Okay. Now, as I run the simulation, they're gonna come down. They're gonna come down, and if there was no friction, only from the understanding of NLM, if all their masses are same, what is the time they're gonna reach? Are they gonna reach at the same time or different times? If there is no friction,
The same time.
they're gonna reach at the same time. Yes, I hope you understood that. If we consider these bodies to be in NLM and we consider this surface to be smooth, and all these bodies were sliding down, not rolling down, okay, sliding down, then they would reach at the same time. You can actually note this down. This is a valid observation. But if there is friction, rotation is going to get involved, right? Rotation is going to get involved. Now, the question is, which of these do you think is going to reach the bottommost location first? Just take a wild guess. And I want everyone to take a participation in this. I want Medha to tell me which one do you think will reach first. It doesn't have to be physics wise, mathematically wise correct, but just tell me, what do you think? Solid sphere is what Rishi says. What does Medha say? Medha says nothing. Medha says solid sphere as well. What about Janvi? What about Ritu? Guys, come on, take a pick. Choose your favorite one. Well, everybody's favorite one seems to be the solid sphere. I don't know why. Solid cylinder. Okay, let's see. Okay, so keep an eye out. I'm going to run the simulation. You tell me which one reaches first. But by the way, red one is the solid sphere, green one is the hollow sphere, and blue one is the the hollow cylinder, and yellow one is going to be the solid cylinder. So I want to see which reaches first and which reaches last if we have friction on this. So I'm going to run the simulation. Okay, so I'm just going to pause just at the moment when they're about to reach. So which one has reached first, guys? Which has reached first? Solid sphere.
Solid sphere.
Yes, your favorite contestant has won. And which one has reached at last?
So the cylindrical shell.
The cylindrical shell, or the hollow cylinder. Okay. Now, in terms of moment of inertia, how do you explain this? That's what we are going to talk about. Okay. So, but remember this result. Let me repeat one more time. Excuse me. Very nice. Okay. So just for viewing pleasure, one more time. Okay, watch how the solid sphere reaches down first. Very nice. Okay, so let's stop this madness and let's go back to our actual studies. Are you able to see my whiteboard?
Yes, sir.
Okay, so in this whole list of moment of inertia, notice the solid sphere, the moment of inertia values. Okay, so this is essentially what this I think is equals to 0.4 mr squared. So this is the reason I'm doing it in decimals. It becomes easier to watch. 2 by 3 is essentially 0.66 mr squared. This is like 0.5 mr squared, right? This is also 0.5 mr squared. All of these are like just 1 mr square. Okay, so these were the contestants. Don't look at those the sticks one. There was no stick rolling down the incline. Among all of this, which do you think has the least moment of inertia? Among this entire list, which has the least moment of inertia?
So the solid sphere.
The solid sphere. Okay, and it reached first. So okay, I need you to understand this one. Moment of inertia is essentially a measure of how easy it is to rotate something. Something that has low moment of inertia will be very easy to rotate. And that is the reason when we allowed rotation, solid sphere came first because its moment of inertia was least. Now, this you can also draw a parallel, observation from the linear mechanics. In linear mechanics, we know mass represents inertia. Inertia is directly proportional to mass. Now, think of this. If you have the same amount of force, something that has higher mass will be difficult to accelerate, right? And something with lower mass will be very easy to accelerate. Same thing happens in rotation. If you apply a same amount of torque, and it had like in an inclined plane, all of them had the same amount of torque because they had the same mass and hence the same friction and so on. We'll talk about this at a later time. But yeah, when you have the same amount of torque, something that has lower moment of inertia will be very high to accelerate or angular accelerate, if that makes sense. It will be very easy for someone with lower moment of inertia to rotate versus something that has very high moment of inertia. It will be very difficult to rotate, and that is the precise reason why the hollow cylinder reached last, because its moment of inertia among all of the contestants where was the highest. Please let me know if you got the significance of what moment of inertia is.
Yes, I got it.
Got it? Okay. Now let's move forward to finding out moment of inertia for irregular bodies. Okay. Now, the regular bodies that we have defined, it's a very limited case. It's a very limited case scenario. It just gives us the moment of inertia about the center of mass, but it's not essential that you always rotate something about the center of mass. There could be other possibilities as well, right? So how do you deal with situations like that? Well, you have two theorems for it. Well, the first one is called the parallel axis theorem. The parallel axis theorem, okay? The parallel axis theorem. Okay. Now, I'm going to highlight a few points where students make most mistakes. So I'll inculcate that in the definition itself. Ah, this cup of tea is heavenly. Where is the... Yes. Okay. So in this, you need a few things. Like, for example, you have a body and you know where the center of mass is. And you also know what is the moment of inertia about an axis that is passing through the center of mass, and we are going to call it ICM. Here, CM represents center of mass. Okay. Now, imagine we know for a body, the moment of inertia that is passing through the center of mass is ICM. And I want to find out the moment of inertia about an axis which is at a distance of d, and it is parallel. As the name suggests, this theorem is only valid for parallel axis. So you need, you can only find it along parallel axes. You cannot find it like any random axis. You can't do it. Okay. Now, I'm going to write the theorem like this. If we know the moment of inertia about the center of mass axis, about the axis passing through center of mass, and we need to find out moment of inertia about another parallel axis which is at a distance of d. Then I is equals to ICM plus MD square. I equals to ICM plus MD square. This is the formula that you have to remember. There is no mathematical derivation for this. This is a theorem. You got to remember it. However, we can use it to prove some things. Like, for example, did you write this formula? Have you noted it down? I'm going to move forward. Okay, but please remember, there are two important, points here. One is that they should be parallel. The axis should be parallel. And you should know the moment of inertia of ICM. It cannot be any axis. It has to be ICM, just means axis through center of mass. The major mistakes that students make here is that instead of ICM, they take the center of, the moment of inertia about any random axis and try to apply this formula, but that way they get it wrong. Okay. So let's see if this works, if this formula works. Okay. So I'm going to the next slide, guys. If you let me know if you have noted this down.
Yes, sir. Okay.
Okay. Now, we know the moment of the center of mass of a rod is located where, guys? If we have a uniform rod of mass m and length L, where is the moment of where is the center of mass of this rod?
It's at L/2.
It is at L/2. It is exactly in the middle. This is where the center of mass is. Okay. So my question to you is: do we know the moment of inertia of this of this rod through an axis which is passing through the center of mass? Do we know this?
Yes, sir.
Yes, it is equals to ml squared by 12, right? Now, let's say I want to find out the moment of inertia about an axis which is parallel to this center of mass axis, but it is at a distance of L/2. So that means it's on the edge. Can we find it out well using the formula? Well, I is equals to ICM plus mass of the body into distance ka square. So this will be what, guys? What should I put ICM? ml squared by 12. Mass of the rod is m, and the distance is L/2 ka square. Distance between the two axes is L/2 ka square. So you'll have ml squared by 12 plus ml squared by 4. Guys, can you add this up and tell me how much this is?
So ml square by 3.
ml squared by 3. So the LCM is 12, and 1 plus 3 is 4, right? So you get ml squared by 3. But isn't this the result that you already knew?
Yes,
right?
sir.
You already knew this. You derived it before only. So this gives us a little bit of intuition into what exactly we are doing. If you know the moment of inertia about the center of mass axis, you can pretty much find out the moment of inertia about multiple other axes. Like, for example, this scenario. Okay. Usually any normal person would rotate a disk about its center. But what if instead of rotating about the center, you started rotating about this point? So if you try to rotate this disk about this point, this is how it would look in the next instant. Okay. Like this is how it will look. And after that, this is how it will rotate. I hope you are able to understand. This is the next how it will rotate. Then it will go like this. Do you understand what is going to happen?
Yes, sir.
Okay. So my question to you guys is this only. If you have a disk, where's the insert button? Yeah. If you have a disk, okay, if you have a disk and you try to rotate it about an axis, this is an axis which is perpendicular to the plane passing through the edge. You have to find out moment of inertia. You have to find out moment of inertia. Go for it, guys. Would you like to know how it looks from the side view? Well, let me just make it. Where did it go? This is how it will look from the side. This, which is circular in nature, from the side is going to look like this. This is how the axis is. Okay, from the side view. This is the side view. This is top view. So how do you do this question? Well, at the center, we know the moment of inertia if this axis was passing through the center of mass, right? If this was passing through the center of mass, the moment of inertia would be mr squared by 2. This is something that you have already derived. So if you use the formula I equals to ICM plus md square, right? The mass of this disk is m, and the distance between these two axes is how much, guys? This is actually equals to r. The distance between these two axes is equals to r, right? So you'll write something like m into r square by 2. This is the moment of inertia about the center of mass. And then you just add m into r square. So 1 plus half is just 3 by 2. 3 by 2 mr square. Okay. So this is going to be the moment of inertia. I think a lot of you got it correctly. Okay. Few of you made a mistake as well. Please let me know. Yes. Was it a silly
Got it,
mistake?
sir.
Okay. Now I could ask you more questions. Let's up the difficulty a little bit. Okay. Let's say we have some random body like this. Okay. And I know that the moment, this is where the center of mass is. I don't know the moment of inertia about the center of mass, but I know the moment of inertia of a axis, which is like, uh, you know, let's say r distance from it. Okay. So what will be the moment of inertia of a body of about an axis which is at a distance of 2r from it? So let me reframe the question. Okay. So the moment of inertia of a body is I naught about an axis that is r distance away from center of mass. So what will be the moment of inertia about an axis that is 2r distance from center of mass? Very nice. Okay, so all of you are giving me answers. So yeah, let me see how the question is done. Please let me know which of if there was a mistake, what kind of mistake you made. Okay, it's always important to know what kind of mistakes you are making. It's like, is it a calculation error, which is very okay. Like, it's okay to make calculation errors at this point, because with practice that resolves. But if you are having you're thinking of a wrong concept, and then and you thought you know the concept you're applying, but you're applying something different, is actually the ones that you need to focus more on, because those are the ones that will teach you. Okay, if you are making a mistake and you are looking at how to actually do this, that's the way forward. But anyway, look at the solution. Okay, so we know the formula I is equals to ICM plus m into d square. Now for the first axis right here, let's call this x. Okay, we know the moment of inertia is I naught. Okay, so this will be like I naught is equals to ICM plus m into r square. From here you will realize that ICM is actually I naught minus mr square. Does this make sense, guys? See, in the first segment, the moment of inertia is I naught about an axis that is r distance away from center of mass. Okay, it's r distance away from center of mass. So the thing is that when I'm writing this equation, I naught should be on the left hand side. Okay, I naught is the moment of inertia, and we don't know what is the moment of inertia about the center of mass. So I'm first trying to find out what is the center of mass moment of inertia. It's I naught minus mr square. Now for the second case, where this axis y axis is actually you know 2r distance away from the center of mass axis. Again, if I write I equals to ICM plus md square, this is something that we do not know, so I'll just write I. ICM ka value, I'm going to write it as I naught minus mr square. And in place of md square, now these two axes are at a distance of 2r. So I'm just going to plug in 2r ka whole square, right? So this is going to be I naught minus mr square plus 4mr square. So your answer will be I naught plus 3mr square. Awesome. So some of you got it correctly, guys. Some of you got it correctly, some of you made a small mistake. Okay, but I think a lot of you got it correctly. Yeah, did, right? So people who made mistake, please let me know where you are making mistake, right? Please understand this formula is only valid when you have access to center of mass ka moment of inertia, and we use the first condition to actually find out the center of mass ka moment of inertia, the moment of inertia about the center of mass. Once we have this ICM, then only I can apply that formula and move ahead. Please let me know if you understood this one. If you have any doubts, I can repeat, but you gotta ask. You gotta ask. Okay. Okay, I assume everybody understood. Okay. But yes. Yeah, silly mistakes, it is okay. Yes, Purva, it is okay to make silly mistakes. And things will improve over time as you do more and more questions. Getting rid of silly errors or those kind of small mistakes it's like the easiest stuff. Getting rid of calculation errors is the easiest stuff. All you need to do is a little bit more practice, and over time you will do that. So yeah, no need to worry about this, right? So that's the end of the parallel axis theorem. Now I'm not doing it for every other body, but you have a list of moment of inertias. Now that means you can find out moment of inertia about edges of everything. Like if you rotate the ring about the edge, disk about the edge, cylinder about the edge, hollow sphere about the edge. We have been only talking about rotating the bodies about the center of mass, but what about rotating them about the edge? Well, this is where the parallel axis theorem comes into play. Okay. Now, the next one we want to talk about is perpendicular axis theorem, right? The perpendicular axis theorem. Where did it go? Yep, the red color. The perpendicular axis theorem. Okay. Now, in perpendicular axis theorem, it's more limited usage compared to the parallel one. And when I say limited usage, I mean you cannot apply it for everybody. Okay. Every it's only valid. First of all, it's only valid for 2D structures like a plate, a ring, or something like that, or a triangular plate, square plates. So it's like 2D structure based. This theorem is only 2D structure based. And the second thing is that although it's always true, it is only useful if for symmetrical bodies, because that is when in symmetrical bodies is when you have another equation to help you actually solve for moment of inertia. And what I mean by that, again, it will become clear over time. But yeah, please understand moment, the perpendicular axis theorem is actually a little bit more, limited usage compared to the parallel axis theorem. Where parallel axis theorem can be applied for anybody, perpendicular axis theorem is mostly for 2D planar objects, and it's very limited. Okay, I'm using the word limited too much. Okay, so perpendicular axis theorem says something like this: like if you have a symmetrical body like this, and if you consider that x and y are in the plane of the planar structure, like here we are considering a disk. Okay, then obviously, guys, tell me what is the direction of z? What is the direction of z? Is it
They're
going
mutually
like this?
perpendicular to x and y.
Yes, guys, some of you might believe is z is in this direction and the angle here is like, I don't know, 120 degrees or something, but it is not true. When you make z like this, you actually mean that z is coming out of the screen. So you have to remember cross product a cross b comes out of the plane. In cross product, when you do x cross y, you're supposed to get z. X cross y gives you z. So that means once you define x and then you define y, you can always find out the value of z, and that z is actually coming outward. Okay, it is coming out of the plane. So that is the moment of inertia about z. Okay, so that's the z-axis. So how do you actually represent a vector which is coming out of the plane? Well, you make a circle with a dot. This means the vector is coming out of the plane, right? And if you make a circle with a cross in it, you mean that the vector is actually going in. Okay, I hope this representation makes sense. Now here, we'll make it like this. This is what z is. Okay. Now, perpendicular axis theorem says the moment of inertia about the z-axis is going to be equal to the moment of inertia about x plus the moment of inertia about y. This is what perpendicular axis theorem says. It's a very limited use case scenario where you are saying if you take x and y in the plane of the body which you have, then ix plus iy should always add up to become iz. Okay. Now, my question to you is this: for a symmetrical body about the x and y axis like a disk, okay, does it really matter if you rotate it like this, or why am I doing all this? Wait, I have good shapes. I'm so horrified by the circles I'm making. I don't like these. Yes. Okay. See. Okay. So if I rotate the disk about this axis, okay, the diameter, but remember, it's not passing through and through, and it's not a sphere, it's a disk. It's not passing through and through. Uh do I have this disk with me? Well, I don't have a disk with me. Let me see if I have anything in my drawer. Nothing of that sort. In that case, I have to take help of 3D, or at least GIFs. Can't teach like this. Wait. Yep, found it. Guys, look at this. This is what we're talking about. Okay. No normal person will try to rotate a disc like this. The disc is supposed to rotate about the axle. Okay. What I mean by this is whatever we have found out till now for a disc or a ring, the rotation used to happen like this. Okay, let me do it in a different page so that you're able to understand. This is what we used to do. Okay, the rotation is happening about which axis, guys? It's happening about this axis. Like if I do it using the red color here, this is the axis, and this axis is actually coming out of the plane, right? This whole wheel is actually rotating about this particular axis, right? But if
Won't
you
it be
just
immaterial if it's coming out or going in this
huh?
case? So won't
What?
it be the same if it's going in or coming out?
Yeah, it will be same. Yeah, true, that is true. Okay, now in this scenario though, the moment the rotation is actually happening about this axis, which is actually in the plane of the wheel, and it's going to be slightly different. Okay, so this is what we are calling iy. Okay, now my question to you is this: is iy going to be different than ix? Okay, now what do I mean by that? Well, let me draw it one more time. Okay. uh, okay, this is my proposition. Okay, this is my proposition. I have a axis like this. This is iy, and this thing is rotating like this. It's kind of making me dizzy, to be honest. So let's do it really, really fast. Guys, do not look at that. Yes, just let me know if ix and iy will be similar. The relative ease with which you can rotate the body, rotate these bodies, because it's symmetrical in nature. It's symmetrical in nature. I think Ix and
That will
Iy
be the same.
value will be same. Yes or no, guys? Please let me
Yes,
know if
sir.
you understood this one.
So, but isn't moment of inertia scalar?
It's scalar, yeah.
So why value? We can just conclude that they're the same.
I didn't understand.
So you told that the values would be the same. We could also conclude that they would be the same Iy and Ix.
No, I mean, when I say value, I don't mean direction is also there. I just meant the moment of inertia
Okay,
are
sir.
same. Are same. Okay. Now, if the disk was rotating like this, this is the z-axis. This is the z-axis. Can you tell me what is the moment of inertia about the z-axis? That I think we already know for a disk. It is mr squared by 2. By the way, this is actually not a disk. This is a ring. But you get the idea. Okay. So in our discussion, what was happening is we know that Iz is equals to Ix plus Iy. And from symmetricity, I also know that Ix and Iy, they are equal. And this is already known that Iz is equals to mr squared by 2. So using these three information, can we find out the moment of inertia about X? Well, yeah, I can write mr squared by 2 is equals to Ix plus Iy, right? But since both of them are equal, so each of them will be equals to what? Mr squared by 4. It's going to be equals to mr squared by 4. Please let me know if you understood this. Any part you did not understand, please let me know.
Got it, sir.
Okay. There's Rishi saying he got it. What about other folks? Other folks?
Yes, sir.
Got it? Okay, cool. So if you understood this, then find me the moment of inertia of a ring. Yeah, why again? Why? Why am I trying to do this to myself? I can always copy it. Yeah. So this is a ring. I have a question for you. Okay, we have a ring. And I want you to find out the moment of inertia if I try to rotate it about this axis. Okay, it's a ring of mass m and its radius is r. Guys, find out. You gotta use both perpendicular axis theorem and parallel axis theorem in this one. Okay, now I hope you understand how this rotation is gonna look like. Okay, so from the side, it's just gonna look like, a stick going like this, like this, like this, like this. I hope you're able to understand what I'm drawing here. Let me try to make it more intuitive. Uh, yeah, I can do this again. I don't know why I keep. Let's say this is the ring. Okay, and this is the axis. This is the axis. And the axis is actually passing through and through. I'm looking from the side. So this is how it will look. After some time, this is how it will look. Okay. And then after that, this is how this will look. You get the idea what's going to happen. Are you able to understand, guys? Oh my God. I am an artist. I'm a physics artist,
Got it.
guys. OMG. Hmm. Oh, at this point, my goal is no longer teaching you, it's just creating art. So marvel in the beautiful art which I'm creating. My God. I'll probably just get a lot of heat from my boss if he sees me doing this in class. My God. And if you're wondering who my boss is, that's the guy who took last class. Dheeraj sir. Awesome physics teacher. Yes. So I don't know what this is. Now that I look at it from outside, doesn't look as pretty as I hoped it would. Maybe if I make it with different colors, but that's not the focus. Yes. Anybody found out the moment of inertia about this axis?
So I was able to apply parallel axis theorem. Then with perpendicular axis theorem with two variables, I wasn't sure how to proceed.
Okay. My first question to you is, do we know a moment of inertia about the center? Like
Yes,
if there was an axis which was passing through the center, through and through, I mean, into the plane like this,
yes, sir.
do we know the moment of inertia for that? Let's call this Iz. Okay, so that
That'll be
moment,
mr square.
it will be just mr squared. Now use perpendicular axis theorem to tell me how much will be the moment of inertia about this x-axis, about this x-axis. Well, you're gonna say Iz
That'll
is
be
equal
mr square by 2.
Ix plus Iy, but because it's a symmetrical body, we know Ix is equal to Iy, and this is mr squared. So that means this will be equal to 2 times of Ix. So your moment of inertia about the x-axis will be mr squared by 2. Now this x-axis is also the moment of inertia about the center of mass, because remember, in a ring the center of mass is exactly at the center. So this is still the moment of inertia about its center of mass. Now can you tell me what is the distance between these two? Well, it's r, right? So here, this is where you apply the parallel axis theorem, and you say, well, I is ICM plus MD square, right? So ICM is how much, guys? We just found out MR square by 2, and how much is D? R, right? So your answer will be 1 plus half, that's 3 by 2 MR square. Did you get it? Any part you did not understand, feel free to ask. Also, let make this flower a little bit smaller. Oops, don't feel like I can.
So I tried the same thing, but I first applied parallel axis theorem and then perpendicular axis theorem. I got the answer as MR square.
Well, you have to understand the moment of inertia about X and Y would not be same if you do that. Now, imagine you know the moment of inertia at this location and you're calling it IZ, right? Are you saying the moment of inertia about this axis and this axis, right? This axis and this axis is going to be same? No, right?
Yes, I got my error.
You got your mistake?
Yes, sir.
Okay. So, see, again, that's why I told you. This is a very limited use scenario jahan pe you have to know ki Ix equals to Iy. Okay, so that means X and Y should divide the bodies in a symmetrical manner. That can only happen if you take X and Y on the center of mass in this question. Please let me know if you understood this one. Okay, little bit more question on these theorems, and then we are ready to move ahead into the torque equations. Okay, so one more question I have for you guys, which deals with, I don't know if I want to keep this in the notes. Oh my god, it's so ugly. Oh my god. Okay, so if I have a rectangle, okay, if I have a rectangle of length A and width B, okay, so this width right here is B, and this length right here is A. This is A. My question to you is this, okay, if I try to rotate, this sort of rectangle about a line, about an axis that looks like this. Are you able to see the line?
Yes, sir.
Okay, this is the line. Can we have a dotted line? Yes. Can we have a, guys, try. Find out the moment of inertia if I try to rotate this, this rectangle essentially about this axis. So this is how it will rotate. This is how it will rotate. Okay. If you look at the screen, I do have rectangles all around me. So if this is a rectangle, it's blurred. We'll remove the blur. Yep. If this is the rectangle, this is what we are trying to do. It's rotating like this. Oops. I'm gonna hit myself with this. Okay. So please let me know if you found out the answer. How would you proceed? Oh, Namish got the answer correctly for the last question. Very nice. Yes, guys. Okay. Little bit of,
what would be the moment of inertia when it rotates about an axis passing through center of mass?
well, that's what the question is, bro. It is passing through the center of mass.
Yes, sir, but when it passes inward, so we can't use the standard rod formula because it has a
We
width.
can. We just have to a little bit think about this. Okay, so let me ask you this. Let me ask you this, okay? Give it a little bit time, okay? And I have, let's say, a small strip like this, okay? Let me also color it so that you're able to understand what I'm talking about. If I take a very small strip like this, whose length, it's negligible, the mass, let's say, is dm, okay? And essentially, this is a rod, right? This is a uniform rod of length, how much? A, right? Now, answer me this. What will be the small moment of inertia for this rod? Well, let's call this dm1. It's a rod which is rotating about its own center of mass. That black strip is rotating about its own center of mass. So it's going to be dm1 into a square by 2l. Do you agree with me?
Yes,
because if you have a uniform rod of mass m and length l and you try to rotate it about the center, it is ml squared by 12. So why not, consider a small black strip like this whose mass is dm1, length is a. So its moment of inertia would be dm1 into a squared by 12. Yes or no? Yes, no, say something, guys.
Yes, sir.
Okay, now let's take another mass somewhere at the bottom. Let's say this is dm2. What is the length of this mass? Well, A. So what will be its moment of inertia? dm2 into a square by 12. Now, if I want to find out for all the entire, rectangle, so I'll take strips like this everywhere, right? So you'll have something like dm1 plus dm2 plus dm3 and so on. And at the end, all of them will have a square by 12. How much do you think this is? Do you understand, guys? The moment of inertia of a rectangle also, if you try to rotate it about an axis, it will still be what? ma square by 12. Ma square by 12. Did you understand? Did you
Yes,
understand?
sir.
Now I have another question for you in the next page, which is this. Okay, same question, but this time, okay, instead of the axis being like this, it is it's more like yes. Do you understand the proposition here? Do you understand what I'm trying to imply? What if you try to rotate the rectangle? I feel like it's not parallel. It's killing me. Ah, so it's rotating like this. Okay, but this time this length is b. This length is b, and this length is a. Guys, tell me what will be the moment of inertia about this axis. So what will you do this time? Well, this time you're gonna have, again, you're gonna have to imagine some strips like this one. Okay. Now again, the same process. Let the mass of this small strip be m1. And this length this time is how much, guys? How much is this length?
It will be B.
It will be b. So what will the small moment of inertia like I1 will be how much? m1 into b square by 12. So I2 will be what? m2 into b square by 12. So what will be like if you add all those steps, how much will be the net moment of inertia? The total mass into b square by 12. Awesome. Any part you did not understand in these two equations, please let me know. Please let me know if you understood, if you didn't understand any part of this. Okay, my final question regarding this rectangle. Okay, if I want to rotate it about an axis that goes through like this, do you understand what this is? Like if you make the side view of
It's
it.
coming out of the plane.
Yes, it's coming out of it. Okay, so if I make the side view of this, and can I make side view of this? I feel like I can. This is how the side view would look. This is how the side view would look. Okay, and you're trying to rotate the rectangle like this. Find me the moment of inertia about this z-axis. Come on, guys. You can do this. What is the moment of inertia about this? Well, it is equals to what? Ix plus Iy from perpendicular axis theorem. Right? This time they are not equal. Ix and Iy are not equal because they are not symmetrical. But the issue is we already know Ix and Iy. Look at these. We know that along this axis, along the y-axis, the moment of inertia is ma square by 12. And along the x-axis, it's mb square by 12. This we found out in a different way. They are not equal, but we know the values, right? So this is going to be what? M into a square by 12 plus m into b square by 12. So the moment of inertia, if you rotate a rectangle like this, is going to be how much? M into a square plus b square by 12. Please let me know if you understood this one.
Got it, sir.
Got it, guys? Okay, really, really awesome. Now, what we are going to do is leave moment of inertia after we discuss one small last thing. One last small thing we are going to discuss, which is known as the radius of gyration. Okay, it's known as the radius of gyration. Okay. Now, what is radius of gyration? Well, see, for uniform bodies, you can always derive the moment of inertia, right? But what if you have like a fancy body like this? Oops, let's make it less conspicuous. And you don't know, you can't integrate this. You can't integrate this particular a non-uniform or it's not non-uniform. It's just that it's irregular and it's not symmetrical. So doing the integration becomes very, very difficult. So what people do in this scenario is they will find out the moment of inertia practically. They will try to rotate it and then they will see the values of the angular acceleration and torque, and they will find out the value of the moment of inertia. And then they will say, let's say you're trying to rotate it about this axis, and they will give you some value k. They will say k is the radius of gyration. Okay.
But what
And
is gyration?
it's a name. Gyration is a name. Radius of gyration. What
Is
is
it
it?
some phenomenon or something like that?
If you're trying to relate this to gyroscope, then no, I don't think it has a relation to that. Okay. It's just a name. So radius of gyration, main purpose is the use. Let me talk about the use of this. Okay. So if we know that our mass is m and radius of gyration is k, then guys understand this, that the moment of inertia of this body is just gonna be m into k square, m into k square. Okay. Now this is very ideal to us, because if you have a non-uniform body, instead of them expecting you to know its moment of inertia, they are giving you a value k, which when squared and multiplied to mass will give you the moment of inertia of that body about that particular axis. Okay. Now I have a question for you. Okay. What do you think will be the moment, like if you try to find out experimentally, and let's say you have a sphere, if you have a sphere. Okay. uh, you have a sphere like this, solid sphere, it's a solid sphere. What will be its radius of gyration? Well, we know the moment of inertia is 2 by 5 mr square. Okay. And radius of gyration is actually such that if you do m into k square, you should get moment of inertia, which is 2 by 5 mr square. So m cancels and k comes out to be under root of 2 by 5 into r, right? So one second, someone said something. Yeah, root 2 by 5 into r. So this is going to be the value of radius of gyration. Now, what does it physically mean though? It means ki if all of the mass of this solid sphere were to be concentrated at one point such that it would have the same moment of inertia as the whole solid sphere, that distance where you can keep the point mass is known as radius of gyration. So again, let me repeat what I'm trying to say. Like if there was a point mass of m, which was kept uh, at a distance of root 2 by 5 into r distance, it will have the same moment of inertia as a solid sphere. So that's how radius of gyration is defined. It's the distance where if you keep a point mass, if you keep a point mass at that location, then it will have the moment of inertia exactly same as the entire body itself, right? But that's just fancy talk. If you have the value of k, just square it, multiply with mass, you get the moment of inertia. That's the only thing you have to know regarding this. You will see occasionally questions where they will ask you what is the radius of gyration. Just make sure ki mk square is equals to the moment of inertia that you can find. So all of these questions that we did, like for example, this question, all of this could have been masked in the form of saying ki find out the radius of gyration. That means you just have to find out the moment of inertia and equate it to mk square, cancel the m and give the value of k. That's the only catch here. There's nothing more to it. Okay. So that, guys, is the perpendicular axis theorem and also the radius of gyration. So that is pretty much the end of moment of inertia. If you have any doubts regarding any of the topics that we discussed till now, please let me know. Okay. If everybody understood this question, then I have one final question just before you go. Do you know what fidget spinners are? Have you played with one?
Yes, sir.
Okay. Okay. Guys, I have a fidget spinner. No, I don't. I just made a picture of it. Okay. These are symmetrically arranged. Okay. Each disc is of mass m and radius r. Okay. What is the moment of inertia if you try to rotate it about the center? So what is the moment of inertia about? Oh, give it a try, guys. This is the final question from moment of inertia. Guys, try this question, please. Let me know if you understood. Let me know if you find an answer.
So all these are disks.
All these are disks. Yes, guys, anybody found the answer? Okay, so let me explain. For the green disk at the center, which is of mass m and radius r, what will be the moment of inertia? Let's call this 1.
So it will
Let's
be
call,
mr square by 2.
for 1, moment of inertia is essentially mr square by 2. Okay. Now, can you tell me what is the distance between the center of 2 and the axis of rotation? What is this distance?
So 2r.
It's 2r. So to find out the moment of inertia of 2, I'll have to find out what is the moment of inertia about its own center of mass plus mass into distance square, right? That will be how much, guys? This will be mr square by 2 because this is also a disk. If it rotates about its own center of mass, it will be mr square by 2. And the distance from the axis of rotation is m into 2r ka whole square. So that means this is mr square by 2 plus 4mr square. So that means this is going to be how much?
The 9 mr square by 2.
9mr square by 2. Now this is for 2. What about for 3?
So it would be the same.
It will be the same as 2 because again it's at the same distance, guys. The 3 is also at the same distance. It is at a distance of 2r. Okay. So I3 is also going to be equal to I2. And you know what? 4, 5, 6, and 7. So that means there are a total of 6 disks outside. All of them will be equal. All of them will be equal. Okay. And all of them will be equal to 9mr square by 2. So what will be the addition of all of this? Well, it's going to be mr square by 2. That's for the first one. Plus 6 times of 9mr square by 2. Right? So I think this is 6 times of 54 plus 1. It's going to be 55mr square by 2. Yes, guys, please let me know if you understood this. This is the fidget spinner question.
Got it, sir.
Got it? Okay. Now, you have to understand what we are going to do next is this. What is the difference between translation and rotation? Okay, so this is moment of inertia has ended. You can start a new topic. We are transitioning into what exactly is torque and what exactly is the difference between translation and rotation, right? So the topic will be rotation versus translation. Okay, rotation versus translation. So what exactly is rotation and what exactly is translation is what we are going to talk about. Okay, so guys, any ideas on this? What is the difference between them? What is the difference between translation and rotation?
The rotation would be something like how Earth rotates about its own axis, whereas translation would be where there would be actual movement from one point to another.
Okay, cool. In terms of the see again, continuous bodies will be more like can be thought of as system of particles. Hence, the name system of particles has been that means continuous big bodies like a sphere or a disk or whatever we are thinking. It's more of different small particles adding up to become those big particles. My question to you is this: that can we explain translation and rotation in terms of those particles?
So is it that in rotation the position of center of mass doesn't change, whereas in translation it changes?
So, yeah, almost there, almost there. So let me draw and tell you what exactly this what is going to happen. Okay, so where is the so I think to how do you animate this? Well, that is not rotation. Should I like this? Ha, very nice. So if you think about, okay, now I need you to pay attention here, okay? So think of this one point on top of this. When you do have like look at this black spot, okay? This, oh my God, this particular black spot, I want you to look at it when rotation is happening, okay? So and please understand it's going somewhere. Uh, the uh, the discussion is going somewhere, okay? So yeah, have a look at it. Please let me know if you understand. So what is happening to only this black spot I want you to look at is going down and down, okay? So if I make what exactly rotation is, and let me make my own, okay? So what exactly happens is, oh sorry, this point on top has a velocity in this direction because of the rotation, right? And let me use a different color. Blue on red is like not visible. So this point right here on top, and let's call this A, it's moving like this. It's moving like this. Okay. However, this point B right here, it's moving downwards. Okay. And C, on the other hand, the bottommost position is moving backwards. And this point is moving upwards. Now, this is rotation. This is called pure rotation. This phenomena is known as pure rotation. So how do you define pure rotation? It's like all the points on a body are rotating in a circular path about a certain point, and that point is where the axis of rotation is. Okay, so this is like the axis of rotation. So all these points are actually doing circular motion about this point. And even you can take a point here also. This point is also doing a circular motion. How do I know this? Because its velocity will be perpendicular to the axis of rotation. Okay, so this is going to be what the axis. This is pure rotation. This is pure rotation. Okay, so how do you never mind. This is how you represent pure rotation. Please let me know if you understood this one. Yes, this is what I'm
Yes, sir.
talking about. All the particles moving about a certain point, and this is exactly what we are talking about, the rotation part of it. Okay. Now understand what exactly is translation. Translation is more to do with something like this. It's going in a forward direction. So that means each particle, like if the center of mass is actually, let me have it a little bit symmetrical. Yes. If the center of mass is traveling forward with VCM, that means this point A on top will also move forward with the same velocity VCM. This point will also move in the forward direction with VCM. This point at the bottom will also move with VCM. And this point at the end will also move with VCM. This is the meaning of the term translation. Translation means all the particles, they move together in the forward direction. Okay. All of them move together in the forward direction. So this is known as pure translation. This is known as pure translation. Okay. Did you understand what I'm trying to say? There is no relative motion between the particles of a body, then it is known as what? This is known as a translatory motion, because if the center of mass is moving with BCM, all the other particles are also moving with the same velocity. So the body tends to go forward like this. Please let me know if that makes sense. Do you understand the difference between translation and rotation from this? Right? In
Yes, sir.
translation, all the particles are moving relative to each other. They are moving in this way, right? This is known as pure rotation. Whereas in pure translation, all the particles are actually traveling with the exact same velocity, and the relative velocity is actually zero between them. It's zero between them. Now, what will be both rotation and translation? Okay, rotation plus translation. How does it work? Well, you'll have a body which is rolling like this. Okay. And then let me also animate this. Okay, so it is rotating, but it's also moving forward along. It's doing both. I hope that makes sense. Rotation and translation would mean, imagine a car wheel. A car wheel is doing rotation as well as translation. The center of mass of the wheel is moving forward, and also the whole wheel is rotating about the axle. Okay, so if I have to imagine, and this is very, very important, I need you to remember this. If you ever want to analyze the idea of rotation and translation together, the fun part is that you have to think of them separately. Okay, so let's say this body is doing a translation with velocity v, and it's also rotating with a velocity with an angular velocity of omega. Now the unit for velocity is what? Meter per second. Tell me the unit for angular velocity, guys.
Radians per second.
Radian per second. Radian per second. Radian. Radian per second. Thank you. Radian per second. Now think of only the translational part, then tell me the velocity of a point because of the translation. Well, because of translation, and let's also color code this. I want to color code this so that you are able to understand why each of these velocities are coming. Okay. So let me make it a little bit variable. Okay. So we will designate the translational velocity with a different color. Let's do it with blue. Okay, this is blue. And omega with green. Let's do green. Okay, let's do green. This is omega. So because of the translational part of things, can you guys tell me what will be the velocity of A? And I'd like to show you this. If something is translating with VCM, all the velocities all will also be VCM. So use that to tell me the velocity of A point because of translation. It will also be V in this direction, right? Because of let's also do it for point B. Point B ke liye also the velocity will be like this because of translation only. The C point will be like this. B, sorry, this is B. And D point will also be like this. Okay, but because of omega, guys, here the velocity will be something like this, omega into r. Now if you remember, how do you find out the tangential velocity because of angular velocity? You just multiply it with r. V is equals to omega r. The tangential velocity corresponding to rotation is given by omega into r. Guys, tell me what is the direction of omega r at point B?
That will be in the
For,
forward direction.
and
That
for
will be in
that
the tangential direction.
for that I want you to refer to this. Because of rotation, how does the velocities look like? It's tangential, right? So if it's doing both rotation and translation, guys, this is how omega r looks. What about at C point? It will be backwards. And what about at D point? Omega r will look like this. Very nice, right? So when rotation and translation are happening together, the net velocity of each location will actually be different. Each point on that particle, on that rotating and translating correspondingly, like they're rotating and translating together, then the velocities of each point will actually be different. Like for example, at this location, the net velocity would actually just be V plus omega r, right? At this location, C location, however, the velocity would be how much, guys? This will be V minus omega r. Can you tell me the velocity at B point? It will actually be under root of V square plus omega square r square. Why? Because these two vectors are now 90 degree to each other. How do you add two vectors that are 90 degree to each other? V square plus omega square r square under root, right? So this is what the net velocity of this particle look like. Okay, this is where the net velocity of the particle will look like. Let me draw it here. V square plus omega square r square. So in a way, you have to understand that this point, D point right here, it's actually not going up, neither is it going forward. It is going somewhere in between. Now, I want to show you a simulation that will make this even more interesting. Okay. Somebody dropped. Hmm? 9. Guys, can you let me know what's going on in your math right now? Math, which topic is being taught?
So we are doing straight lines.
Straight lines, which portions?
So we finished locus and we are doing the types of represent the different types of writing the equation of line, like point form, point slope form, and slope intercept form.
Okay,
So give us the forms, and in the next class we'll be doing questions on them.
Okay, thanks for the info. Okay, so there's going to be a wheel, and there's going to be a point on the wheel which is marked. Okay, and we will see how that single point on that wheel is marked. Okay, so I'm going to run the simulation, and you tell me if you understand what is going on here. You can see the simulation, right?
Yes, sir.
Okay, so when a body is doing both translation as well as rotation, okay, the velocity of the particle is not in a circle. That's like the basic thing that I need you to understand. Most people believe when a body is rotating, all the particles are doing circular motion, but that is true only in pure rotation, not in a situation when you have translation involved as well. In that case, what we get is something known as a cycloid. This figure that you see in front of you is essentially known as cycloid. Right now, imagine a situation when now back
So it
to
looks
our
like a sine wave, but a mod of sine.
The mathematical part of it on what exactly the equation is something that you will take up in your mechanical engineering. Okay. But yeah, you can actually try to figure it out if you can express in terms of.
That looks like a mod sine wave.
It looks like it, but for a graph to be mod of sin x, there is something more that you need to prove. Like you have to be able to prove it y equals to sin x, or at least a function of. Okay. So
Yes, sir.
this will only be like writing the equation for it will be required. We will require a lot. That statement, it looks like mod of sin x would be like, I don't mind it, but it is not like mathematically. I'm not sure if that is the case. Okay. So I hope you understood. You saw that the body was going like this. Okay, it was going like this and then coming down. Okay. So I hope you are able to understand this. Now I have a special case called. No, 1 second. Am I audible, guys?
Yes, sir.
Okay. And also, is the screen visible?
Yes, sir.
Okay. Now I want to talk about before we go ahead. Tell me if you understood the topic by solving a question for me. Okay. So let's say I have a body which is traveling ahead with 10 meter per second. Okay. And also let's make it noise looking. Okay. There's a wheel. It is going ahead with 10 meter per second. And it is rotating with an omega that is equals to 5 radian per second. Okay. Now, the overall radius is 2 meters. But what I want you to do is figure out the velocity of a particle which is at a distance of 1 meter from the center. This distance is 1 meter. Okay. So let me draw it properly. Okay. Omega is 5 radian per second. I want you to find out the velocity of a point which is at a distance of 1 meter from the center, right? And the angle that it makes with the horizontal x-axis is actually 30 degrees. So yeah, go ahead. Let me know, what is the velocity of this point P? How much is Vp? Anybody found the answer, or let me know how to do this? Let me know how to start.
So the velocity of P along the horizontal direction would be 10 meter per second.
Mm-hmm.
And then we have to account for the tangential velocity due to the rotation.
Okay.
So that would be 5 into 1.
Huh.
And then the
So,
angle between the two vectors would be 30 degrees.
oh, that is something. Oh yeah, it is true. That is correct. That is correct. Okay.
And then we can find the vector sum and the question is solved.
Yes. So point P will have a translational velocity. Okay, it will have a translational velocity like this. Okay, I'm going to make it one more time. This is like the center. Okay, and this, let's say, is the point P. Okay, so translational velocity is like 10 meter per second as well. So we know this about translational velocity. If translational velocity is given to us, then it keeps on being the same for all the particles. So point P will also be moving forward with 10 meter per second. But the rotational part of things, because it's rotating like this, the velocity because of translation would be perpendicular to the radius, because tangential velocity is supposed to be perpendicular to the radius. Now this is 1 meter and omega is 5 radian per second. So when you do omega into r, it comes out to be just 5 meter per second. Okay. So the velocity because of omega into r will be like this. But think of this. Let's say this is 30 degrees. And then if you join these two lines, can you tell me how much this angle would be? 60, right? So I think this angle will also be equal to how much? 60. So Rishi, I think you thought the angle between the two vectors is 30, but I think this is 60. Please let me know.
Yes, I got it.
Okay, so the angle between these two is 60 degrees, so alternate interior angle. So the angle between these two vectors is what? 60 degree. So how do you find out the net velocity? Well, under root of, if you remember, a square plus b square plus twice ab cos of theta, where theta is the angle between the two vectors. So 10 square plus 5 square plus 2 into 5 into 10 into cos of 60. into cos of 60 degrees. Okay, so this is what we are doing. So again, the answer does not matter, but please let me know if you understood what we did.
Got it, sir.
Sure. Let us continue ahead and let us talk about the next part of this discussion, okay, which is pure ruling. Okay. Now, you have to understand now that we have omega and v. Okay, so let me borrow a diagram that we took. This is the diagram that I wanted to take out. Okay, so this is what we discussed a few seconds ago, right? Let me get rid of this extra stuff. I don't need it. I just need to focus only on v minus omega at the bottom. Okay, now imagine a situation where you rotate something really fast and just put it on the ground. What is going to happen? Can you tell me? Let me
Could you
repeat the
repeat?
question one more time. I have a wheel which I first rotate really fast and slowly put it on the ground. What's going to happen? If it's a frictionless floor, what is going to happen?
Won't the wheel roll forward?
No, it won't. If there is
That is
no,
slip forward.
it won't do anything. It will just rotate on the spot if there is no friction. Okay, if you do this experiment on the ice, that means if your vehicle is on the ice and you put your gas pedal in, or you start accelerating your car, the wheels will rotate on the spot. The car will not move forward because you need friction on the ground to move forward. Do you understand what I'm trying to say here? Right, so the bottommost point has two velocities, one in the forward direction and one in the backward direction. Okay, now when the wheel is rotating really fast and there is not enough velocity, you can say that the bottommost point is actually sliding backwards. It's sliding backwards. Okay, and there is this also this reverse scenario, like for example, you are you have started cruising on ice and suddenly you put the brakes on. Will the car stop? No, it's going to skid ahead. So what's going to happen? There is going to be V, but there is not going to be omega R. Why? Because the wheel will not be rotating because we have put the brakes on. But the wheel will slip forward because there is not enough friction. So in that case, V will be greater than omega R. So guys, please understand there are three scenarios. Scenario number one is when the velocity, translation velocity is greater than omega R. There is also this second scenario when omega R could be greater than V. But when we are on cruising on the highways, with no acceleration involved or no slipping involved, you can say that omega R is pretty much equal to V. This condition is known as pure rolling. This is known as pure rolling. Pure rolling में the bottommost position में the rotation and translation are in sync. Neither is more like it's not disbalanced. Like for example, when a car is drifting, you know what drift is, right? When the car just the wheels are rotating really fast, but the car is not moving as much as it should have. That is known as drifting. Okay. Now in that case, omega R represents how much velocity comes because like how fast is the wheel rotating, right? V is how fast the wheel is moving forward, right? If V and omega R are equal, they are in sync, we call this the pure rolling. But please understand that is only like half of the cases. The rest of the cases, what happens, like for example, when the plane is landing on the runway, can you tell me which of these three conditions is going on there? As soon as it touches the ground, which one of these is correct for those? A, B, C. Which do you think is the correct scenario for that? When a plane is landing on the runway, is V greater than omega R or omega R greater than V or V equals to omega R?
So would V be greater than omega R?
Yes. The velocity of the wheels is really high, Janvi. That's correct. Okay. As soon as it touches down, the rotation of the wheel will not be as much because it does not have like a engine to run that wheels. The wheels are just free running, and there's just the only reason we have wheels is to apply brakes on the wheels, right? But as soon as it touches the ground, the velocity is really high and the rotation is not as much. So as soon as the wheel touches the ground, essentially for some part of it, the wheel just slips. It slips on the ground, okay, creating like a like a smoke, little bit of smoke comes out. So when you see, if you have seen a plane land, you'll know as soon as it lands, there's a smoke. There's like it burns the rubber. That's because the wheel, instead of rolling, it starts sliding in the beginning and slowly starts gaining rotational velocity as well, and then it matches the velocity with which is moving forward. So v becomes equals to omega r eventually, but initially v is greater than r. Okay, I have another question. Imagine a car is just about to start the race, and as soon as it hits the accelerator pedal, the wheels rotate really fast, but it is not moving as, or think of a scenario when the car is stuck inside sand or mud. Okay, car is stuck in mud or sand, and the wheels are rotating really fast, but it's not going as much forward. Which do you think will be valid? Which case will be valid there?
So case B.
Case B. Okay, case B will be valid there, right? Do you understand this now? Yes. Case B will be valid because when in sand or mud, the wheels of the car will be rotating really fast. So omega r will be much greater, but the velocity of the wheel will not be as much. Okay. So what is pure rolling then? Pure rolling is that scenario when rotation and velocity are in complete sync. Okay, they are in complete sync and there is no slipping involved. There's no slipping involved. Okay. Pure rolling means no slipping. No slipping. Okay, and also you can also think of this. See, if v equals to omega r, guys, what will be the motion, or what will be the velocity of the bottommost point? If
That will be
v
0.
equals, it will be zero. It will be zero, right? Guys, you have to understand, in pure rolling, the body comes, like the lowermost point is at temporary rest. It comes to rest temporarily. Okay, now I want you to look at the simulation that we talked about one more time. Okay, I want you to understand that when the body is just at the lowermost point, do you see that this thing is coming down, and then becomes almost vertical at this point, and then again rises up? So do you understand that there has to be a point here where the velocity has become zero, because it was going down and then it started coming up? So that means the velocity has to become zero. Do you understand what I'm trying to say here, guys? So the
Yes, sir.
particle, when it reaches the bottommost position, is at temporary rest when it is doing pure rolling. When it is doing pure rolling. So in pure rolling, guys, in pure rolling, what happens is that the lowermost position on the wheel, okay, it's going to be at temporary rest. Okay, so these are the two vectors which are changing. I'm also putting in the vectors here. Okay, let me just show the first, only the rotation velocity. This is how the rotational velocity works. Okay, and if I show only the translational velocity is always moving forward. It's always pointing forwards, right? Now both of them together, the net velocity will look something like this. The net velocity will look something like this. So again, here you can see at the bottommost point, the velocity, the net velocity kind of disappears. Okay, let me try to pause it at that moment. Do you see the net velocity almost disappears at this point? Okay, so that is what I was trying to say. I hope you understood. If you didn't, please let me know. So the condition, what is the condition for pure rolling, guys? What is the condition of pure rolling? If you ever see a scenario where they say there is no slipping, or if they say there is pure rolling, the conditions that you can say that are true, the conditions that you can apply is either say v is equals to omega r. You can also say a equals to alpha r. Now, do you remember what a and alpha are? Well, a to everybody remembers. If you differentiate this function, velocity becomes acceleration. But what is the rate of change of angular velocity? Well, that is known as
That's
what?
alpha.
Angular acceleration. So rate of change of angular velocity is what? Is angular acceleration. Okay, so these are the things that you can, these are the two equations that you can say are true for pure rolling. Okay, so these are the two major equations that we'll be using if you ever come across a situation that says if there is no slipping on the ground or there is pure rolling happening. Please let me know if there is any doubts.
No doubt, sir.
Okay, then let's move ahead. Okay, now this is when the ground is at rest. I would also like to talk about a scenario where, again, the same thing I want to do, but this time, what if this wheel is not on ground, but actually, and let's get rid of this. Is on top of a platform. Okay, it's on top of a platform like this. So let's say there is a platform like this, and the wheel is on top of this platform, but the platform itself is going forward with V1. How do I ensure pure rolling, guys? Tell me. And you know velocity of C point is actually V minus omega r in the forward direction. Or if I want to show the directions, like this is C point ka velocity will be like forward like this. Okay. And omega r will be like backwards like this. And this is for the C point on the wheel. Okay. I'm going to make the platform slightly below so as to again they are actually in contact, but just to make the diagrams visible, I'm going to make it slightly below. Yes, guys, tell me, what do you think? How do you ensure it's doing pure rolling on top of a platform and the platform itself is moving forward? Guys, understand this platform is actually in contact like this, but if I do that, I can't show V and omega r. Okay, so that's why I'm making it slightly below, but actually these are in contact. Okay, this is omega r, sorry. Right. So how do you ensure that pure rolling is happening? Well, pure rolling means that
Like the horizontal velocity is V plus V1.
Yeah, pure rolling means that the lowermost particle on this body is at temporary rest compared to the particle which is below it. Like on road, C would come to rest. Then we will ensure we will understand key. Okay, this is pure rolling. But if you want to be with rest, with respect to the platform, you want the lowermost point to be at rest. So that means the net velocity of C should be equals to V1, right? Let me repeat one more time. See, if you want a block to be on rest on top of a plank and the plank is moving with V1, then the block should also move with V1. No, then only the relative velocity between them would be zero. Do you understand what I'm trying to say? So that means
Yes,
the
sir.
lowermost particle on this should have a velocity of V1 if it wants to be in rest with respect to the platform. So what will we say for this scenario? Well, we will say V minus omega r is actually equals to V1. I hope that makes sense. Right? You want see in case the platform is not moving, V minus omega r is actually equals to 0. So you just say V equals to omega r. But if it is moving and you want it to be at rest, then V minus omega r should have the same velocity, like the C point should have the same velocity as the platform itself in order to be at relative rest. I hope that makes sense. Okay. Please let me know if you have any doubts. Okay. Now, let's talk about torque. Guys, do you know what torque is?
The torque is something that can cause rotation.
True. That is absolutely correct. Torque is something which is the cause of rotation. Torque is the cause of rotation. Okay. Just like force is the cause of linear motion, guys, torque is the cause of rotation. Okay. The symbol for torque is given by this. This is the symbol of torque. This is known as tau. Okay. This SI units for torque is actually Newton meter. And how do you find out torque? Well, this is the formula for it. Now, I've talked about this a little bit in the bridge course. Okay. Please let me know if you remember what cross product is. Do you remember how to do cross product?
Yes, sir.
Yes. How do we do cross product? Like, for example,
So we can represent it in a 3 cross 3 determinant.
No, I mean, like, if you just give it like A cross B, how do you find out the magnitude?
The magnitude would be given by magnitude of A into magnitude of B into the sine of the angle between them.
Awesome. Awesome. If you remember, if I give you two vectors and then I ask you to do A cross B, to find out the magnitude of that vector, the resultant vector, you have to do A ka magnitude, B ka magnitude into sine of theta followed by an R cap. Because remember, cross product, the alternate name for cross product is also known as vector product. Vector product. Why this is known as vector product? Well, when you multiply two vector quantities and get a scalar answer, that is known as a scalar product. And that is something that we did for work. Work was force dot displacement, right? But vector product is when you multiply two vectors and you also get a vector as your answer. So apart from the magnitude, you are also looking at a direction. So A cross B ka magnitude will be A ka magnitude multiplied by B ka magnitude and sine of theta, where theta is the angle between the two vectors. Like for example, this let's say is A and let's say this is B. and the angle between them is theta, then how do you find out cross product? Well, A cross B, A into B into sine of theta, where theta is the angle between them. Now, how do you find out R cap though? Do you remember how to find out R cap? There is something called right hand thumb rule. How many of you remember this? What is
Yes,
right
I
hand thumb
remember.
rule? Yes, I gave notes also. So you point all your fingers in the direction of A and you curl your fingers towards B. Well, in this case, it will be like this. So A will be upwards and cross your fingers, curl your fingers towards B, and your thumb will be pointing into the plane. Okay. And as the name suggests, right hand thumb rule, please use your right hand. Okay, but because if you do it with your left hand, the sense will come completely opposite. So the first thing you need to make sure, and I've seen this happen many times, students are holding their pen on the right hand, so they will just do it with the left hand and get a wrong answer. Okay, but it's a right hand thumb rule. That means it should be done with the right hand. First, point all your fingers towards the first vector, and also one thing you gotta remember is that A cross B is not equal to B cross A. If you remember from cross product, it's not commutative. Well, A
It'll
dot
be
B.
minus of B cross.
Huh. A dot B is equals to B dot A. It's commutative. Dot product is commutative, but cross product is not. It's not. Okay. So make sure you remember this, and also revise through the section where if you have A cross B, but A and B are given in the component form. Like for example, this is 2I plus 3J plus 4K, and this is given as minus 2J plus 4K plus 3K. How do you do A cross B? I think you remember, if you remember, if we make like 3 by 3 slots, this is known as a determinant, and you write I minus J and K on top, and then you write 2, 3, 4, and then you solve it. I want you to revert back to that from the bridge course. It's available on your Learnist. Go to the NEET section and start watching all the initial lectures. Or you could also watch Dheeraj lectures on the same topic. Both of us have delivered exactly the same thing. Okay. Now, again, torque is given by R cross F and not F cross R. Remember, order matters, so it's always R cross F. But what exactly is R though? Anybody knows what R is?
So distance of the particle from the axis of rotation.
Okay, so it's not the distance of the particle per se. If you have a continuous body, then then how will you define R? Right? So it's the vector joining axis of rotation to the location of applied force. Applied force is R vector. It's R vector, guys. Okay. And what is F vector? Obviously force. It's force. Okay. But now we gotta do the questions. If we do the question, then only we'll be able to understand truly what it means. Okay. But if you haven't noted this, please note this. Please note this. Done. Now I have a question for you. Very easy question. Okay. Let's say we are trying to rotate a uniform rod. This is the uniform rod, and I have hinged it here. Now, when I say hinged, what does hinged mean? Well,
So
hinged
then
means
it's constrained to move only along one side.
hinged means I have fixed it here, and the body is allowed only to rotate about this. Like this, like anti-clockwise or clockwise, doesn't really matter. But it can, since I have put a nail inside of this, it's like a door. Like if you're looking at the door from top, this is where it is hinged. It's not like you can rotate about the center, something like this. That would be dangerous. Okay, so it's hinged on one end. Now there are a few forces acting on this rod. Okay, this rod is acted upon by four forces. One F1 is acting here. Okay, at a distance of L by 2, exactly in the middle, there is another force acting downwards, and this is F2. Okay. And again, at a distance of L by 4, there's a force acting downwards, that's F3. And there's a force acting on the end, which is also again at a distance of L by 4. This time it's acting at an angle like this. Sorry, this I messed up. This is F4, and it's making angle theta with the horizontal. Guys, tell me what is the net torque? Net torque. Okay. So please let me know if you understood this. Understood the question, right?
Yes, sir.
Yes. Four forces acting at four different locations. Find out the torque because of each one of them. Also the directions, and then add all of them together. When you find out the the torque because of each forces, you're gonna add all of them to find out the net torque. Yes, guys, are you guys trying? Should I solve it on the board?
Done, sir.
Done? Okay, cool. So let me tell you how to do this. Okay, it's hinged here. It's hinged here. Okay. So first of all, let's find out what is the torque because of force F1. Guys, torque is given by distance from the axis cross
Will
F.
be 0.
It would be 0 in this case because force is acting on the axis of rotation itself. The body is supposed to rotate about this hinge, right? Now, what is the distance of the force from the hinge? 0. It is passing exactly through it. Okay, so there is no distance between the hinge and the force. So the torque because of the first force is 0. What about the second one? What about the second one? The second force F2 is at a distance of L by 2 here. So this is going to be how much, guys?
From minus F2 into L by 4.
L by 2 into F2 and sine of 90 degrees. Sine of 90 degrees because if you consider this to be R, and let me show you the different color.
So would it be
This,
negative?
well, we'll talk about it. One second, one second. If this is R and F is downwards, so R is how much, guys? It's going to be L by 2, and the angle between them is 90 degrees. So L by 2 into F2 into sine 90. So that's how much magnitude-wise it is going to be F2 into L by 2. All of you understood this one? Right, now the direction part of this. If you do R, point all your fingers in the direction of R and curl towards F2, you'll see that your thumb is pointing into the plane. So rather than writing minus or plus, I would suggest writing like this. What does it mean? It means that the torque is into the plane. It is into the plane, right? Does that make sense? Yes?
Yes, sir.
Okay. Now let's talk about torque 3. Torque 3. The third force is at how much distance from the axis of rotation, guys? It is at a distance of L by 2 plus L by 4. That's 3L by 4. So your torque is going to be 3L by 4 into F3 into sine 90 because again, the angle between the R vector and F3 vector is how much, guys? It is 90. So sine 90 is 1. So again, this value is going to be F3, 3L by 4. Okay, so I'll write like this, 3L by 4 into F3 in upward direction, outward direction. How do I know it's outward direction? Point all your fingers in the direction of R, curl towards F3, and the thumb is pointing out of the plane. So that means this particular torque is coming out of the plane, right? What about torque 4, guys? Torque 4 will be F4 into L, but this time the angle between the vectors is theta, so you will have sine theta at the end. So F4 into L into sine theta. Okay, now what is the direction of this? Again, I think it's going to be R cross F outward. It's going to be outward. It's going to be outward. Now, this is one way of doing it. There's a lot other ways. Now, if you want to find out the net torque, you know, key two of the torques are coming out, so you'll have to add them and then subtract the one that is going inside. Okay. So the net torque will be what? Torque 4 plus torque 3 minus torque 2. Okay, this is how it is supposed to be done. But there are different ways of thinking about this. What do I mean by that? See, most of the time you don't have to do that cross product. You don't just have to think about what is the sense of rotation that is created by these forces. Like for example, F2 force, if it's hinged at this location on the left end of the rod, F2 is trying to rotate this body in which sense? Is it trying to rotate it clockwise or anti-clockwise? It's trying to rotate it clockwise, right? Look at F3. F3 is trying to rotate this anti-clockwise and F4 is also trying to rotate it anti-clockwise. So when you finally find out the net torque, you are seeing that I am adding torque number 4 and torque number 3 and I subtract torque number 2. And I subtract torque number 2. Does that make sense? Does that make sense? So in a way, when you are actually finding out net torque, you don't have to do R cross F. Most of the time, you just need to see in which sense is the rotation happening. Is it happening clockwise or it's happening anti-clockwise? That's what you have to check. Please let me know if you have any doubt in this one. Okay. Please let me know if you have any doubts in this one.
No doubt, sir.
No doubts? Okay. Now, Now that you know how to find out torque, let us also talk about something called the torque equilibrium. The torque equilibrium. Okay. Now, how do you remember how do you define force equilibrium?
So when the net force is zero.
Yes, when the net force is zero, okay, then we say that the body is in force equilibrium. Okay, force is in we say that the body is in force equilibrium and the net acceleration would be zero, and then it will not move linearly. Okay, if it is at rest, it will remain at rest. If it's at constant velocity, it will remain in that constant velocity. So it will not change its motion, is what force equilibrium means. Now, what exactly torque equilibrium means? Well, a body in torque equilibrium would mean that the net torque on a body is equals to zero. So this would mean that the body will not have any angular acceleration. So if it is at rest, it will remain at rest. If it is rotating with a constant angular velocity, it will continue to remain in that sort of angular rotation. Okay, it will remain in that angular rotation. Now, my question to you guys is this though. If we have net force equals to zero, does it imply net torque is also zero? Like if I have a body and I know the net force acting on that body is zero, does it mean that the net torque on that body will also be zero? That's something that I wanted to ask. Well, the answer is no. You can't imply that. And I'll give you a counter case to prove it wrong. Why? Let me show you. Let's say there is a rod, and I apply, let's say equal and opposite force, one here and one here. Both of them are 10 Newton. Okay, 10 Newton force in both directions, equal and opposite. What will be the net X? What is the net force, guys? What is the net force?
Zero.
Zero. But what about the net torque? Is it zero? Net torque is
No,
zero?
sir.
No, it is not. Why? Because you can understand that this thing is going to rotate. It's going to rotate in a circular motion, right? Yes. And if you do consider this to be 1 meter and this continue to, you understand that this is also 1 meter, then I can actually find out how much net torque is. For example, the torque on the left hand side is going to be how much, guys? It's going to be 10 Newton meter. This is also going to be 10 Newton meter. But if you think about it, the directional sense of both these torques are in the same way. They're both trying to rotate in the same direction. So the net torque is actually going to be equal to 20 Newton meter, right? So one thing I need you to understand that force equilibrium does not imply torque equilibrium. They are separate. They're kind of independent of one another. Okay, can you give me an example when net torque is zero, but net force is not zero? Like you have rotational equilibrium or torque equilibrium, but you don't have force equilibrium. Can you give me a situation like example like that? Think of this. This is not that difficult, guys. Come on.
The body being accelerated in the horizontal direction.
True, true. Awesome. What about other folks? Janvi, what do you think? If you have a wheel, and let's say this is the wheel, okay, and it's on ground like this, okay, and this, let's say, is the center. Guys, if you apply a force directly in line with this particular center of mass, what do you think will be the rotation of this body? And again, smooth ground. Okay. This is a scenario where this force is going to create an acceleration. Let's say the mass is m, then force will be equal to mass into acceleration, and there will be acceleration. It will be F by m. But guys, can you tell me how much is the torque for this? Torque will be F cross R. Again, guys, remember, there is R here. This is R. This is F. But I still say the torque is zero. Can you tell me why the torque is zero?
So they are in the same direction, the two vectors.
How much is theta?
Zero.
Nope.
There's 180 here.
Yes. Theta is 180 degrees because force and R are in opposite directions. So when you do FR sine theta sine 180 degrees, the torque comes out to be zero. The torque comes out to be zero. Okay. So this is a scenario when you have a rotational equilibrium or torque equilibrium, but not force equilibrium. Okay. So this is what I wanted to tell, that these are independent scenarios, independent conditions. So this is not happening. Okay. So that being said, if you have any doubts in whatever we have discussed till now, please let me know. Okay. Please let me know. If not, then I have a question for you guys. Okay. So let me draw the question. And you look back and let me know if you have any doubts in any part of it. Guys, so this is a question. I have, like, this is the floor. Okay, this is the floor. Okay, and this is the vertical wall. This is like the side view. This is the vertical wall, and this is the floor. And I have a stick. Okay, the stick goes. Okay. And I have kept the stick somewhat like this. I've kept the stick somewhat like this. I'm gonna change the color of the stick. Stick is
So we have
brown.
done a similar question in math.
In maths, wow,
Yes, sir. So the stick slides and we have to find the locus of the midpoint.
wow, yeah. But this time a little bit more physics, less math. But that's a decent question. But this time, what I have is, okay, you guys know if this floor is smooth, tell me what will happen. If the floor is smooth, the stick will just slide over, like this end will move this way and this end will move this way and the stick will just fall down. Yes. But I'm saying
Yes.
it has some mu. It has that bare minimum mu for which, the stick is stable. Okay. So this is actually the objective of the question. Okay. Theta is given to us. Theta is given to us. Okay. And you got to figure out, and also like the mass is m and the length is l. This angle is theta. Tell me what is that minimum value of mu for which this particular system is stable. The stick is stable on the floor and the vertical wall, and it does not slide down and fall. Did you understand the question?
Yes, sir.
Okay, go ahead. 2 minutes to try this. But do you want me to do it or you guys are trying it? Please let me know if you're trying, then I'll give you 1 more minute. 1 more minute, not more than that. Okay,
I
that
think
is,
you can solve it.
huh?
I think you can solve it.
Okay, cool. Okay, so what are the things that we can, for example, a question like this. First thing is you make the FBD. You make the FBD for this. Okay. So if I copy this and I paste it somewhere else, and I want to talk about what are the different forces acting on this block, then all of you are sure ki, okay, mg will be acting downwards at the center of this rod. Mg is something that is acting downwards. Okay. What other forces do you know? Okay, there's going to be a normal like from here, because its contact is in contact with the floor. So normal will be like upwards. Yes, guys. Yes or
Yes,
no?
sir. One from
And
the bottom.
there's also going to be a friction like backwards like this. And also this end is in contact with the vertical wall. So, okay, sorry, I should not erase this. I'll just move it from here till here. Okay. So if it is in contact with the wall also provides a normal from that direction. And this is something we're going to call N1, just to differentiate it from the other normal provided by the ground. Right? And this is the extent of it. There is no other force acting on this, right? These are the four forces which are acting on this block. And if we have to find the answer, it will come from all these four forces only. There's nothing else here. Okay. Now, one thing we know that if this is equilibrium, then one thing we can say is that normal is equals to capital Mg. And we can also say F equals to N1. Can we say that, guys? Yes? No? This is force equilibrium. about y-axis, right? And this is force equilibrium along the x-axis. But you can see these two equations are not sufficient for me to find out what is the value of friction. Because N1 is something that we do not know, and friction is also something that we do not know. Okay, none of these things we know. So we need another equation to solve for the value of F or N1, right? One equation to connect F to N1 or any way to find out the value of N1 or F. Okay, now that is where the torque equilibrium equation comes in, right? You can say that the torque above any of the point on this particular stick will add up to become zero. It will add up to become zero, right? Now, where do you think is the most beneficial point where I should take the net torque to be equal to zero? Which point do you think makes my life easier? I could take it anywhere I want. I could take outside for that matter. Okay. But you tell me, where should I take it so that I get the maximum benefit out of it? Just like choosing origination. Huh? Where?
The center of mass of stick.
Okay. Again, see, if I'll give you possibilities. Okay. You can take it. Yeah. Whatever you said is also.
Or at the contact surface, it would be easier.
Yes. This is what I'm looking at. If I take the torque about this point, two of the forces are passing through this hinge point, the point which is on contact with the floor. Normal and friction, both of them are passing through this point. So when you find out the torque because of friction and torque because of N will be how much?
Zero.
It will be zero. Okay. So it's just like choosing the origin in center of mass. You take the center of mass ka origin wherever you get the most benefit out of it. Right. So here the maximum number of forces are passing through the bottommost location. So it is beneficial for us to take it there. Okay. Take it there. Okay. But we'll also require the angles. Can you tell me how much this angle is? If I make it here, if this is theta, guys, how much will be this? If this will also be theta. Awesome. Can you tell me what will be this angle? Now, if you should remember this from inclined plane, this should be theta, because this component would be how much? Mg cos theta, and the one parallel to it becomes mg sin theta. Do you remember this?
Yes, sir.
Okay. Now, let me take the components of these forces. N ka component along this will be how much? N1 sin theta, yes? And the component of N1 along this will be equals to N1 cos theta. Yes or no, guys? What about mg? This is how much? Mg cos theta. And about the plane, this is going to be how much? Mg sin theta. Now let's talk about torque. When I take components like this is another way of finding out torque, and components make it real easy to figure out which of these components will actually play a role in giving torque to that body. So N1 cos theta and N1 sin theta, which do you think is capable of rotating this body? N1 cos theta or N1 sin theta?
N1 sin theta.
N1 sin theta. Just because this is the force perpendicular to R. If a force is 180 degrees or 0 degrees, like if it is parallel to the R, then that force component will not contribute towards torque. That's something that we know, right? So this N1 cos theta and mg sin theta are not going to provide any torque. Well, also, can you tell me what is the distance though? Like what is the distance from here till here? That's L by 2, right? The total length was given as L. And what is the distance where N1 sin theta is acting? What is this total length from here to here? Well, that's equal to L, right? So if I do write the torque equation, okay, and I want to write it in a different page, so I'll just take it there. So can we do that? Okay, I have it. Okay, so I'll just make it a little bit cleaner so that you can understand which forces we are dealing with. I'm erasing the redundant stuff. Oops, I should not have this. Okay. So this arrow is also something we don't need. We know this force is acting at a distance of L, and this force is acting at a distance of L by 2. So when I finally write the torque net equals to 0 wala equation, I say what? Mg cos theta into L by 2, because this is the torque. Force into R. Mg cos theta into L by 2. And then minus N1 sin theta into L should be equals to 0. Tell me, why did I put minus sign in between? That's because the rotational sense of these two forces are different. This is, and mg cos theta is trying to rotate it like anti-clockwise, and 1 sin theta is trying to rotate it clockwise. So these torques are in different directions, so I have to subtract them, right? You can also go from the basics and find out where by doing the right hand thumb rule, R cross F is into the plane for N1 sin theta, right? And for mg cos theta, R cross F is out. It's coming out of the plane. It's coming out of the plane. Okay. So because again, from there also you can understand these two torques are in opposite direction. That's the reason we are subtracting them. So when we equate them, guys, when I equate them, L cancels. And from here, you'll be able to find out the value of N1. N1 will be equals to mg cos theta by 2 sin theta. Guys, tell me if this makes sense. Yes or no, guys?
Yes, sir.
Okay, now let's go back to the previous equation where we said कि friction is actually equals to N1. So friction ka value will be equals to how much? Mg cos theta divided by 2 sine theta. But I think we can simplify this further. Why? We don't even need the value of capital M here. We can still simplify it further because the first equation says कि normal is equals to mg. Normal equals to mg, right? So in this scenario, normal is equals to mg, and friction can be written as mu into normal is equals to, but and normal is mg, so I'm just going to write mu into mg is equals to mg cos theta by sine theta. So from here, mg and mg cancels. So guys, can you tell me what is the value of mu? Mu will be equals to, and I think I missed out a 2 here. There's a 2 here, I forgot. So this is going to be 1 by 2 tan theta. Please let me know if this makes sense. Any part you did not understand, feel free to ask. Yes, no? Okay. Let us continue to the next segment of this. We can do more questions on equilibrium. We'll do this next class as well. Okay. But I would like to introduce the concept of torque equation. How do you write an equation like the second law for linear mechanics? How do you translate that to, how do you convert it to the rotational form is what we want to discuss next. Okay. Okay. So write down the next topic. It's torque equation. Guys, let me know if you have any doubt. Let's say we have a body like this, any continuous body, which is made up of different particles, hence the name system of particles. Okay. And let's say this whole body is doing a rotation like this. And like we have discussed, if a body does a rotation about a certain axis of rotation, all its particles are doing what kind of motion, guys? They are doing circular motion about this axis of rotation. So this particle right here on the body will be doing a circular motion like this. Similarly, if I take another mass like this is also going to do a circular motion like this. Another mass, if you take like this is also going to do circular motion like this. So I hope you are able to understand that each of these masses, M1, M2, M1, M2, and M3, all of these are actually going to do small circular motion. If the whole body is doing a rotational force, you can think of them, the whole body as being made up of small particles, and each particle is doing a circular motion. Each particle is doing a circular motion. Please let me know if you understand the context of this.
Yes.
Okay. Okay. Now, let's say if this is rotating with some angular acceleration alpha, can you tell me what is the acceleration of each particle? The tangential acceleration of each particle? Well, alpha into r, right? Now, for the first mass, it is going to be alpha into r1. For the second particle, it's going to be alpha into r2. Third particle is going to be alpha into r3. Please let me know if you understood this.
Yes, sir, got it.
Okay. Now, look at this. If I want to talk about what is the force, what is the tangential force on each particle, then the first.
So each of them would be unequal?
Huh? The force on each particle will be different because their accelerations are different, right? So M1 into alpha, but remember, alpha will be same for all the particles. When a body is rotating with alpha, angular acceleration alpha, that alpha is same throughout. All the particles will be rotating with the same angular acceleration. It's like we have done this in circular motion also. Like for example, if a mass or a disk like this is rotating with some omega, let's say it's 1 radian or 2 radian per second. 2 radian per second. A particle which is at a distance of 1 meter will have how much velocity? 2 meter per second, right? But if you take a point at 2 meters from the center, what will be its tangential velocity? 2 to the 4 meter per second. So when a body is doing rotation, it's not necessary for all the particles to have the same velocity, but it is necessary to have same angular velocity. I hope that makes sense. Okay, so yeah, something like these, I think you should just note it down in your own words because I'm not writing it. Chances are you will forget. Okay. The force on the first particle is going to be M1 into the tangential force on the first particle. So this is going to be how much? M1 into alpha into R1. Guys, tell me if this makes sense. Yes, no? What about the force on the second particle? M2 into alpha into R2. Yes, Now, if you want to visualize how these forces are acting, this force is acting like this. Like it's the force which is responsible for creating this circular motion. So this is like F1. I'm trying to find out. This is F2. This is F3. Please let me know if that makes sense. This is the force acting on this. Now, how do you find out torque one? Well, you'll see, sir, it is actually equals to R1 into F1, because torque is what? R cross F, that we have already studied. Okay, so that is nothing but what? R1 into M1 into alpha into R1. So if I rearrange this, what does it become? M1 R1 square into alpha. Tell me what will be torque 2? Well, M2 R2 square alpha. What is torque 3? M3 R3 square into alpha. So what will be torque net? Well, M. Now, what is the addition of MR square plus M2 R2 square plus M3 R3 square? What is MR square? Moment of inertia, right? The moment of
Yes.
inertia of the body into the angular acceleration. So this is the rotational equivalent of second law. Now I have shown this all this derivation, that's math, but you could have also guessed this equation. You know why? Because you know F is equals to mass into acceleration. This is second law. What is the force equivalent in rotation? Well, it's torque. So force becomes torque. What is the equivalent of mass in rotational mechanics? This is what we started with today, right?
Moment of inertia.
Inertia is directly, it's just like mass. Its inertia is directly mass. Moment of inertia is essentially the mass equivalent in rotation. So mass becomes what? Capital I. And what is acceleration in rotation? Angular acceleration, right? So this is the equation that you have to remember. This is the equation that you have to remember. Okay. And please let me know if you have any doubt in this. You have any doubt in this?
No, sir.
Okay. Now let us do some easy questions followed by difficult questions. Okay. I'll give you first I'll give you a very easy questions. Okay. So very easy question. I have a body, and this is where the center is. Obviously, you know what the center is. And the radius of this ball is essentially uh, is half a meter. Okay. And there are different forces acting on this body. Okay. So on top here, there's a force like this, F. Okay. And that's equals to 10 Newton. And there is also a force here. Okay. And this is actually like this. And I hope you know how much this angle is. This is like 45 degrees. This angle right here is 45 degrees. Okay. So this force is equals to 20 root 2, 20 root 2 Newton. Okay. There's also a force again at 45 degrees, but this time the force is like this. And this is equals to 30 Newton. So my question to you is this. At t equals to 20 seconds, what is the angular velocity? What is the angular velocity? Also, what is the angular acceleration? Okay, so I hope you are able to understand the question. Okay, so at the end of 20 seconds, what is the angular velocity and what is the angular acceleration? Okay, the body is supposed to rotate only about its center. That's given in the question. It's not going to move forward or backward. It's just going to rotate about its own center. We have put a hinge at the center so that the body is not allowed to move forward. It's just rotating at its own location. That's given in the question. Okay, no, that's not how it's supposed to. Yes. So guys, find me that after omega, what is going to be, after t 20 seconds, what is going to be the value of omega and alpha? I hope you're able to understand the question, guys.
Yes, sir.
Yes, guys, anybody found out the value of omega? Do you want me to solve?
1 minute, sir.
1 minute. Okay. My turn to solve this. Please let me know if you messed out something. Okay. First of all, see, I need to figure out how much these forces are applying torque. Okay. So it is given to us that the radius is 0.5 meter. And the first force, the 10 Newton force, which acting on the top is making 90 degrees with the radius, right? So the torque because of the 10 Newton force is going to be like 10 into 0.5. And because the angle is 90 degrees, so just sine 90 is 1. And this is going to be equals to 5 Newton meter. 5 Newton meter. And this is a torque that's trying to rotate the ball in clockwise manner, right? What about the torque because of the 30 Newton force? Well, you can see 30 Newton is actually, it is, actually, it has some R is equals to 0.5, but you can see R and F are in the same direction. It's in the same direction, right? So you can pretty much understand that 30 Newton will not contribute to any torque because the R vector, the vector which is joining the the axis of rotation to the force makes 0 degrees with the force itself. So the torque is going to be 0. The torque is going to be 0. What about the third force? For the third force, it is at an angle. So first we have to take the components. Components one in the direction of in a tangential direction like this. So if I make a line like this, I hope you understand that this angle is going to be 45 degrees as well. Is going to make 45 degrees as well. So that means the components of these force are 20 Newton in this direction and also 20 Newton in this direction. Guys, can you tell me which of these forces will actually have torque? Which will create torque? Like both of them are 20,
So the
but the one which
tangential
is
one.
the tangential one, okay? So, and that is going to be equals to 20 into 0.5, which is nothing but 10 Newton meter. What is the sense of this rotation? Is it clockwise or anti-clockwise? This is also
Clockwise.
clockwise. So what is the net torque, guys? The net torque is going to be 15 Newton meter. Now, once we have torque, to find out alpha, just divide torque by the moment of inertia. Okay. Now, if we consider this to be a body with a mass m and radius 0.5, it is basketballs are hollow spheres, right? So this will be essentially 15 Newton meter divided by 2 by 3 m into 0.5 ka square. So this is going to be your alpha. Now, I think I forgot to give the value of m. But how much does basketball weigh? I don't know. I don't know the official standards, but let's say 1 kg. Okay.
Half a
So if
kg.
how much?
It's about half a kg.
Okay, half a kg also works. Okay, so if it's half kgs, then I think this will become how much? I think 2.5 is going to cancel out. So 3 into 15 divided by 0.5 ka square. So whatever this is, again, I'm not concerned with the calculation as long as you're able to understand what alpha, how to find out alpha. Right now, once you have found out alpha, can we find out omega at 20 seconds? Well, we can use the kinematics equations. We know final omega is what? Initial omega plus alpha into t. What is this formula? This is just v equals to u plus at, guys. We did this in rotational
Yes, sir, we
kinetics.
did this.
We did this, right? In circular motion, final omega is initial omega plus alpha t. Now, if nothing is given, you have to understand that this ball initially was at rest. So take initial omega as 0. Final omega is something that we need to find out. Alpha we just found out and t is 20 seconds. Plug in the values and you'll get the answer. Please let me know if you have any doubts. Nice. No doubts. Now, do you want to do a slightly more difficult question? This is too easy. This is easy peasy, lemon squeezy.
Yes, sir.
Okay. So for a difficult question, what we are going to do is we are also going to involve acceleration. Okay, we're also going to involve acceleration. So in the beginning, I think I showed you that GIF or that sort of, okay, let me bring that GIF one more time. I only used it to qualitatively explain what moment of inertia is. But now what we are going to do is essentially mathematically prove it. What we said is true. Like something that has the lowest moment of inertia will roll down the fastest. That's something that I want to prove using math. Okay. So do you remember the simulation? What do you think the yellow body is? What is this yellow body?
So the hollow cylinder.
Nope. The yellow
You mean
body,
the one
which
that
is
is
the yellow body reaches first.
that's a solid sphere.
That's a solid sphere, right? Why solid sphere? Because solid sphere has the lowest moment of inertia, right? It has the lowest moment of inertia among all of them. And that is the reason it's really easy to rotate it. So that's the reason it reaches first. But we got to mathematically show it that the acceleration is highest for the yellow body. Okay. So for that, what we'll do is we'll take up a simple scenario. where let me insert some diagrams here. Where is the right
So all
triangle?
of them should be of equal mass.
Yeah, all of them. Again, when we are comparing scenarios like that, we have to consider equal masses. So I'll just copy this to the next slide. Okay. Today we are running out of slides like anything. Okay. Uh, Insert, and then you have the. This is the inclined plane. Okay, and let's do it generally without assuming it's a sphere, because we have multiple options here. So to solve this question, what we will do is we'll initially consider a body of just moment of inertia I and solve the entire thing. And then after that, later on, we'll plug in the values of I, and then we'll find out for different bodies what is the acceleration for each of these bodies. Okay, so stay with me. Okay, we're gonna do this, and as soon as we change the color of this, very nice. Okay, now forget. There are a few assumptions that you need to understand. For example, the moment of inertia is taken as let's say this is the moment of inertia is mi. Its mass is m. Okay, the mass is m, and the radius is r, and the moment of inertia is I. Now, moment of inertia for a ring is mr square. For a disk is mr square by 2. For a sphere is 2 by 3 and 2 by 5. All of that we will plug in at the end. I want to solve it generally for any body which has moment of inertia I. Okay. Now, how do I solve this? Now, for example, if there is no friction, solving this becomes just easy because we have done this in NLM. What we do, we just say, okay, the force which is parallel to this inclined plane will be how much, guys? This is going to be mg sine theta, right? If this angle right here is theta, then the force that is parallel to this inclined plane is mg sine theta. I should not be drawing it here itself. I have to make a separate FBD. Okay, always make separate FBDs so that you're able to understand. So this is what this is something like mg sine theta acting in this direction. Okay, and there is mg cos theta acting in this direction. Mg cos theta is acting in this direction, and this is what this is normal acting in the upward direction. Okay, so if there was no friction, then this would have been the FBD, and along this direction, along the direction perpendicular to the plane, you'll be applying Newton's first law, and you'll be saying that normal is equals to mg cos theta, and that's pretty much it. And in the horizontal direction, you're going to say mg sine theta is equals to mass into acceleration. So the acceleration of a body on a frictionless plane will be simply g sine theta. Does that make sense, guys? If there is no friction, first case, if there is no friction. Yes, no, say something, come on.
Yes, sir.
Okay, now if there is friction, there is going to be an additional friction acting in the backward direction. Yes or no?
Yes, sir.
Okay, friction is going to act in the backward direction. Then what will be your second law? Will you say mg sine theta minus f is equals to mass into acceleration? Yes or no, guys? Yes, no?
Yes, sir.
Okay, now mg sine theta minus f equals to ma. Your first intuition will be to say that sir, f is equals to mu into m. But I have told this repeatedly in your when I was teaching friction, that friction ka maximum value is mu into n. It's not necessary that the friction acting on the block will be mu into n, unless we know that the block is sliding off. But this is not sliding. It is what? It is rolling. Do you remember? In rolling, we had this idea that the lowermost point when a body is rolling is at instantaneous rest. It's temporarily at rest. So the friction that is acting here is not kinetic friction, it's static friction. Okay, and that static
Every
friction.
time we are talking about rolling, it has to be assumed as pure rolling.
Pure rolling. We were talking about pure rolling. Okay, so here you will mention if pure rolling is happening. Okay, what can you say about alpha and A? What is the relationship between A and alpha? We did this. Today's class we did it. Tell me.
So A is equal to R into alpha.
Awesome. A equals to alpha into R. Does that make sense, guys? A equals to alpha into R. Now I'm going to write the equation for torque because I have written the equation for force, second law of force along the parallel plane. Can you tell me how will I write the equation for torque? Well, I'm going to say something like this. What is the torque because of normal mg cos theta and mg sin theta? What is the torque because of all these three forces? They're going to be zero. Why? Because the body is rotating about its center of mass, and all these forces are actually passing through the center of mass. For R for these forces is essentially zero. They pass through the axis of rotation. So the torque because of each of these forces is zero. The only force which is providing the torque is the friction force, and it is equals to how much? F into R. Please let me know if that makes sense. Right? But torque is also equals to, so Fr is equals to torque, but torque is also equals to I into alpha, right? So from here, how much is the value of friction? Well, I into alpha by R. Guys, can I also write it as I into A by R square? Because A equals to alpha R. So alpha would be equal to A by R. I just plug that value in here, right? So this is my second equation. So I got my second equation and I got my first equation. First equation is from NLM. See, remember, we have come into rotational, but it does not mean NLM formulas go invalid. They are still valid. Okay. Now, can we solve these two equations, guys? Can we solve these two equations? And find me the value of acceleration? Well, we can. Okay. So I'm going to take these two equations with me to the next page. Oops. Why is it not selecting? Okay, never mind. We'll take only one with us. If you don't want to join me, well, it's on you. Mg sine theta minus F is equals to mass into acceleration, and friction is equals to IA by R square. Friction is equals to IA by R square. So these are the two equations that we are trying to solve. These are the two equations we are trying to solve. Let me just quickly cross check. IA by R square. Yes, it is correct. Now, if you plug in that value, mg sine theta minus IA by R square will be equals to mass times acceleration. So take this term that side. So this becomes mg sine theta is equals to, if I take A common, this becomes I by R squared plus M. Yes or no, guys? Yes, no? So if you,
Yes,
I want to make this even prettier. So I'm going to divide both sides by mass. So G sine theta is equals to A I by MR square plus 1. What did I do? I divided both sides by M. Both sides I divided by M. Okay. So your acceleration comes out to be how much? It comes out to be G sine theta. It comes out to be G sine theta divided by 1 plus I by MR square. I by MR square. Okay. Last phase. Only 5 minutes left, guys. Now, all you need to do is find me the acceleration for a ring. Find me the acceleration for a disk. Find me the acceleration for a hollow sphere, and find me an acceleration for a solid sphere. All you have to do is, see, G sine theta 1 MR square not going to change. Only plug in the values of I. Plug in the values of I and give me what is the acceleration of each of these blocks. And also find out acceleration of a frictionless cube. Frictionless cube. Okay. The one that is not rolling is just sliding over it. That's just D sine theta. We talked about this before only. Right? So tell me the moment of inertia, the acceleration of the ring. Well, it's going to be G sine theta divided by 1 plus MR square by MR square, because moment of inertia for a ring is MR square. So it's going to be how much, guys? G sine theta by 2, or it's like 0.5 G sine theta. 0.5 G sine theta, right? This scale, how much, guys? G sine theta 1 plus half, right? Yes or no, guys?
Yes.
So it's going to be 2 by 3 G sine theta, like 0.6 G sine theta. Just giving you some numbers to, compare it with. For a hollow sphere, this is going to be G sine theta 1 plus how much, guys? 2 by 3. For a hollow sphere, is 2 by 3 MR square, right? So it's going to be how much? 3 plus 2, 5. So 3 by 5. 3 by 5 G sine theta, which is like 0.6. 0.6 G sine theta. Okay. Am I doing this correctly? Yes, I am. Okay. Solid sphere. G sine theta 1 plus 2 by 5. Guys, tell me how much is this? 5 by 7, yes?
Yes, sir.
5 by 7 G sine theta. Can someone tell me how much is 5 by 7?
So approximately 0.7.
0.7, right? So now you can mathematically see that simulation happening. You can see among all the acceleration, which acceleration among all these 4 contestants is highest? Solid sphere. It has an acceleration equals to 0.7, close to 0.71 G sine theta. So you can see the simulation right here, where the solid sphere reaches first because its acceleration is actually the highest among all the others compared to all the others, right? So you can see the lowest one is that of a hollow cylinder or a ring, right? And you can check that in your numbers as well. For a ring, it's 0.5 G sine theta. Among all the contestants there, 0.5 G sine theta seems to be the lowest. Okay, but compare these to a block which is coming down on a frictionless surface, guys, that is going to be just G sine theta. That's much more. It's even faster than a solid sphere. So rolling is always going to be slower compared to a smooth surface when the block is just sliding off. Okay. So remember those values rather than remembering the direct formula here. I think what you should do is remember the process, because sometimes they can also ask you friction, right? Remember how we eliminated friction to find out acceleration? They can also ask you to find out friction. So remember the process, not the final answer. Okay. With that, guys, what I will do is take a leave for today, and see you next week. Keep enjoying, keep doing physics. Okay. And I'll be sending the recording for this session uh, and the notes as well. So see you next time, guys. Thank you so much.
Thank you, sir.